Hello guys, today we're going to learn, or this weekend actually, we're going to learn about pedigrees. So here we go. So this is a pedigree, and a pedigree shows the passage of traits, usually only one trait, from a family tree. So females are circles, here's a female, and squares are males. A line down represents their children. So person 1 and the little circle woman here, they had 2 children, 3, this one here, and this male here, so they had a daughter and a son, and they obviously married and had children themselves. When you're tracking a trait, when the circle is filled in, circle or square is filled in, that means they have the trait, and when the circle or square is not filled in, that means they do not have the trait. So to follow traits in a pedigree or to predict the genotype of individuals, the first step is to fill in all recessive individuals. Remember, because they have to be little r, or whatever letter you're using, and then use the rest to determine the unknowns. There's possibilities that there could be people that could be more than one genotype, and you can't figure them out based on the data in the pedigree. But the steps are fill in all the recessive individuals, and then determine the unknowns. So we're going to try a few together. Alright, so here's a pedigree. You can see that I drew it, my lovely handwriting. So the example says that the trait that we are tracking is dominant. Okay, so that means all the filled in squares, so this guy, this guy, this guy, or girl, obviously, they are dominant. So that means all the ones that are not shaded are recessive. And when you're recessive, you have to have little letters. So I'm going to use R, because R is easy to write. And I'm used to writing R from the last presentation. So I'm going to write in all little r's for all the people that are recessive. Remember, in this pedigree, the trait is dominant, so all the ones that are shaded have the dominant trait. So I did that. So now we have to use our sort of backwards Punnett square thinking and think, okay, so what could be what does the genotype of person 1 have to be? Well, since they have some people, one child that shows a dominant trait, see this person right here, child number 4, this male has to be big R, little r. And the reason why that is, they have a child that has a dominant trait, so there has to be a little r allele in there. And then some of the children show the recessive trait. So we got person 1. Now let's go to person 3. Well, we see that we have some people that have the dominant trait and some people that have the recessive trait. So they have to be, they have to be this. Otherwise, if they weren't heterozygous, we would not be able to have this one child here. Because they have to have a little r, both have to have little r's for them to have a child that has both little r's and therefore shows the recessive trait. Then we go over here. And if we take a look by here, this one is unknown. Okay, we're probably pretty sure that it's this, but that's not necessarily true. It could just be luck of the draw that they got all children that showed the recessive trait. So we're not really sure. We're not positive that it's big R, big R. We have a strong probability, but if they had another child and then it showed the dominant trait, then we would know that it would have to be big R, little r. So for this one, we're not completely sure here. This pedigree is a little bit different because in this case, the trait that we're tracking is recessive. So in that case, all the filled in individuals are little r, little r. So I'm going to begin filling in all the little r people. There we go. And I know I just love the letter R for some reason. Okay, so now that we filled in all the recessive people, and notice the difference here, the trait that we're tracking is recessive. In the previous pedigree, it was dominant. So that determines who is going to be recessive, the filled in ones or the ones that are not filled in. So let's look at the people they want us to find. We found 2, little r, little r. Now we have to go to 4. Now whenever there's sort of a mix, in order to show both genotypes or both phenotypes, the other parent has to be heterozygous because they have to have a big R and a little r. So in order to have this mix of babies, that has to be the case. If it was little r, then they could only have filled in people. And if it was big R, they couldn't have these two babies here. So then they want us to go to person 10. Now, person 10 is dominant, but since this person doesn't have a big R, they have to be big R, little r. Now, person 12 is interesting. So person 12, if you take a look, they're from this family here. And they have a recessive child here. So in order to have a recessive child, you must be heterozygous. Because in order to have a recessive trait, every parent must at least carry the recessive trait in order to have a baby that shows the recessive trait. And then 13 must also be big R, little r. And that is the Punnett square for this family. Okay, so now, sometimes they can give you a pedigree, and they can ask you, what is the likely mode of inheritance for this pedigree? So we've learned several modes of inheritance. We've learned straight, dominant, recessive, and the other one is sex-linked, and we're also going to learn a little bit later mitochondrial inheritance. But looking at a mode of inheritance, looking at a pedigree, you need to be able to determine, is it likely sex-linked, is it trait recessive, is it trait dominant? So let's take a look at this. So modes of inheritance, autosomal recessive, means it's not on the sex chromosomes, it's on the body chromosomes, or the 22 pairs of other chromosomes. Autosomal dominant, which means the trait is dominant and not sex-linked. Sex-linked recessive, which means the trait is on the X chromosome and recessive. And then sex-linked dominant, which means the trait is on the X chromosome and dominant. Alright, so for autosomal recessive traits, traits that are recessive occur less often, and they often skip generations. And this is the key. So two parents with the trait, so if they're both filled in and it's recessive, must give the trait to all their kids. Okay, so if you have two parents that have the trait, and it's recessive, they must give the trait to all their kids. All their kids have to be recessive. And I guess the only other hint for autosomal dominant traits is that autosomal dominant traits occur more often. So when we're looking at a pedigree, you want to find a section of the pedigree where parents either both have the trait or both do not have the trait. So we're going to look for a pedigree, look at that area. And then we're going to first assume that the trait is dominant. And we're going to assume that all dominant people are heterozygous, and see if it's possible. And then we're going to assume that the trait is recessive and that all dominant people are also heterozygous, and see if it's possible. So we're going to go through one, because this is a little confusing. We'll go through one and it will make more sense. Alright, so these are small pedigrees. I apologize, Miss Flaherty interrupted us, but I'm back. So we're going to first assume that the trait is dominant. And we're going to assume, so here let's assume the trait is dominant. So that is, we're going to assume that he's heterozygous dominant. And then since these guys are recessive, that would have to be that, and that can't work. These two can't have this child. So obviously, this trait has to be recessive and not dominant. This doesn't work. In this pedigree, we're going to assume the same thing now, that these are this, and then these guys, since they're recessive, have to be this, little r, and this is possible here. But we're also going to, for the purposes we're going to just assume the other way, just to make sure, because sometimes you can't tell from a pedigree. So I'm going to erase, and let's assume the other way. So we'll assume, let me get the pointer back, pointer options, pen. We'll assume in this case that these are little r, and that these are big R, and you'll see that that's not possible. These two cannot have this child. So in this pedigree, the trait is dominant. In this pedigree here, these, you can't actually tell for sure. This one is likely to be dominant since all the individuals have the trait, but you can't tell for sure. They could all be recessive. And this one you can't tell either. You can try it. You'll see that either way is possible. So sometimes when the pedigree is small, you don't have enough individuals to tell for sure. Okay, so now I'd like you to take a second and try to figure out whether this one is autosomal dominant or autosomal recessive. I want you to focus on this part of the tree to figure it out. Notice that both parents either have the trait or don't have it, depending upon whether it's dominant or recessive. So I want you to pause the video for a second, really pause the video, and try to figure it out. And then when you think you figured it out, unpause the video, and I will come and discuss this part of the pedigree. Okay, so hopefully you've looked at the Punnett square. We're going to first assume that the trait is dominant. So these guys, although filled in ones, we're going to assume they're heterozygous. Okay, and that means all the other people have to be little r. You'll see that this is in fact not possible. These two cannot have 1 and 3, or 1 and 2 cannot have babies 1 and 3. If we assume the other way, let me get my eraser out. Pointer options, eraser. Okay. Okay, if we assume the other way, so that these guys are little r, and everyone else, we assume these guys are this is in fact possible. If we did a Punnett square, we would see that actually the ratio is actually almost exactly, this would be a 3 to 1, 3 dominant, 1 recessive. So it's pretty close, but obviously this is possible. So now we're going to write the genotypes of the people that we know. So we know that this one is little r, this one is little r, and this one is little r. Okay, now this one, because they have a recessive child, that's an R, because they have a recessive child, this one has to be big r. And because they have a recessive child, this one has to be big r. And hence all the people on the Punnett square are figured out. Alright, so here's another one. And this time I want you to focus on this part of the family. And I'm going to pause the video, you're going to pause the video and do the Punnett square. We have 3 minutes left, and then I'm going to have to make another video because these videos are limited to 15 minutes. So do the Punnett square and figure out, or do the pedigree, and figure out whether this is an autosomal recessive and autosomal dominant trait. And then write the genotypes of the people that you know. Okay, so let's first assume that the trait is dominant. So we're going to assume that all of these people are big R, big R, big R. And then we'll see, if we did a Punnett square, we would see that this is possible. So it's possible to have these kids. If we did it the other way, these would all have to be little r, and then it would be impossible to have these as children. So the trait is autosomal dominant, because if 7 and 8 were recessive, they couldn't have 12 and 11. Alright, so now we're going to figure out, we'll stick to this part of the Punnett square just to keep it within, within the time. So all the ones that are white have to be little r. Okay, and then here, these have to be heterozygous, and the reason why they have to be heterozygous is because this guy is not, it's a guy, this guy doesn't have the big R trait. So one of the little r's has to come from dad here. And then these guys are also little r. And you can figure out the rest of this Punnett square for yourself, or not Punnett square, I'm sorry, pedigree for yourself.
Like a robot.
So sometimes you can't have parents that either don't have it or do have it, or the pedigree doesn't have enough data. So the only things you can sort of see is that recessive traits occur less often, and traits that skip generations are usually recessive. But to absolutely sure, you have to go through the entire pedigree and assume each possibility. But the AP test will not give you such Punnett squares. So now I'm going to upload this video to YouTube, and then I'm going to have part 2 where we look at pedigrees and sex-linked traits. So go to part 2 of this video.